a wire having a uniform linear charge density lambda is bent into the shape shown right here. Find the electric potential at point O. Okay, so here's what we've got. We've got a wire, and it's 2R. From here to here is 2R. And this is all along like the same line here. And then we've got a wire stretched around in a semicircle. Try to draw a circle there. And then stretched out over 2R on this side. So this side and this side are symmetrical, and then we've got R here. And this all has charge on it. Okay, like it could be positive or negative, but we'll just say it's positive. Positive charge lambda all the way around here. Okay, and we want to know what is the potential at this point right here. Now think about it. If this thing's got positive charge smeared all over it uniformly, what I'm going to do is I'm going to take a positive test charge from infinity and work against the electric field of all these guys. And so what the potential is how much work I had to do to take a positive test charge way over here and push it against that electric. Okay, now I'm here. How much work did that take per unit charge on my test charge? That's what I want to know, the potential at that position. Okay, well, let's break this up into 3 parts. The potential due to this charge plus the potential due to the charge on the semicircle. Now, then I'm going to argue by symmetry that the work it takes to get an object here working against the electric field due to the charges here is going to be the same as this. So that what I'm going to do is take this result and just double it. Okay, so, well, let's solve. Let's do this guy first. Now, I know the equation for a point charge. I'm going to take a little tiny chunk of charge right there. I'm going to call that dq. And I know that a little tiny bit of work to get it here, the potential there, okay, which I'm going to call dV, a little tiny chunk of potential is the work I got to do against this charge. And this acts like a point charge. And the potential due to a point charge is K times the charge over R. Okay, so this is the basic equation for the potential of a point charge. KQ over R. But in this case, our Q is a differential Q. It's a little tiny bit of Q. And of course, what we're going to do from here to here is we're going to integrate and add them all up, and then we'll get the work for all of this. Now, I can't integrate this yet because Q and R need to be in terms of the same variable. Okay, so, well, what I can do is make this an x-axis. And so I can say that a little tiny bit of charge is going to be equal to lambda times a little bitty change in length. Does that make sense? Because what is lambda? It's charge per unit length. So I take a charge per unit length, and I multiply that by a little tiny length, I get a little tiny charge. So that's going to be my dq right there. Now R is just going to be x. And then I need to decide where I'm going to integrate from. And by the way, on this one, it doesn't matter. I'll make this positive x in this direction. It doesn't really matter. So I'm going to go from here out to here when I integrate. So this is going to be delta V. And I'm going to go in this direction. I'm going to start here. I mean, I could have easily done it. I probably should have done it on this side. But I'm going to take the k out of the integral. And here's my dq. It's going to be lambda dx over x. And I'm going to go this way, and I'm going to start at r. And I'm going to go all the way out to, well, how far away is this? It's going to be 3r, because here's 1r, and this has a length of 2r. So that's going to be 3r away from my location. Okay, well, so let's play with this. This becomes k lambda times the integral of dx over x from r to 3r. Well, what is the integral of dx over x? Yeah, that is the natural log, isn't it? Right? So delta v is going to be equal to k lambda times the natural log of x evaluated from r to 3r. So this is equal to k lambda times the natural log of 3r minus the natural log of r. Now, do you remember the natural log rules? Right? This becomes a division problem. K lambda times the natural log of 3r over r. Is that right? And so the r's will cancel. And so you get a voltage of k lambda times the natural log of 3. Okay? Now, this thing on the other side takes just as much work to work against the electric field of this guy as it did for this guy. So now what I'm going to do to include this is I'm just going to multiply this by 2. So I'm going to say the delta V for both of these guys is just going to be 2k lambda times the natural log of 3. So this is the potential due to these straight wire parts. Now we have to do this. And this turns out, yes?
When you're multiplying it by 2, isn't one in like a negative direction and the other in the positive direction?
No, this has positive charge on it. And also, hey, remember what's true about voltage. Okay, the question was about direction. Voltage is a scalar. That's the beauty of it. It doesn't have a direction associated with it. If this has positive charge smeared on it, and here's my little positive test charge way over here, I got to do work again. I'm gaining voltage as I do work against that electric field. Same is true with this. I'm doing work. So, so they're going to add. They're going to add because this has positive charge and this is positive charge. Okay, now we gotta do the same thing now for this part. Well, choose a little dq. There's my dq. So let's see if I have room over here. So dv is equal to k dq over r. Okay, that's the basic equation. So let's do this. This is going to be k. Now what is dq? Or what is actually, let's see. dq is still lambda, I'm going to call it here, is lambda, and I'm going to call this a little arc length. I'm going to call that ds. And ds is just the arc length from here to here. And so k d cubed becomes k lambda times ds. And then how far away is my dq from here to here? Well, it's not x anymore. What is it? In fact, all of them are the same r away. Oops, I'm off screen. Tell me. Okay. So this becomes a little bit easier. This change in voltage is going to be equal to k lambda over r times the sum of all my little ds's. Now, I don't really need to integrate this, right? Because when I add up all my little ds's, what am I going to get? Yeah, which is 2 pi r divided by 2, which is pi r. So the voltage that I get here is equal to k lambda over r times pi r. So the r's will cancel. And let's see. I think I'm doing everything right here. Okay, so delta V is equal to k lambda, or k, put constants of nature out front just by, and then this constant right here. And so I'm going to add these two together. So the total delta V, maybe I can call, I don't know, delta V to the, I should subscript these delta V's to keep them straight, but I can't think of a good, how about, I'll just put a little whoop here and a little whoop whoop there. All right. It's just that, so we have 2k lambda times the natural log of 3 plus k pi lambda. And I can just leave it like that, but if you look in the back of the book, they just pull common factors out. You've got a k and a lambda in both of them, right? So k lambda, and then I think they put the pi first. Pi plus 2 times the natural log of 3. And is that what they... Yeah. And that is our answer. Okay. So, yeah, this requires a little integration. It's a hard one. Any questions? One last thing is that, again, this is an example of how this class can really help you in your AP Calculus classes, because you are actually using it, though, to do something that's real. All right, that's enough.